My name is Terry Honan. I'm from Blinn College in Bryan, Texas. This is a two-year school in Bryan College Station, Texas, which is where Texas A&M is. So we're largely a feeder school for A&M. The title is Use of Mathematica and CDF to Create and Distribute Interactive Physics Lecture Notes. A little long of a title there. But the gist is to discuss the lecture notes, the interactive lecture notes, and the tools used to create them. I think for a crowd of people teaching physics, the tools may prove useful. And I'll discuss future plans for sharing these things. Okay, so the outline is we'll first discuss the lecture notes, brief overview and examples, and then the drawing tools and future prospects and possibilities for sharing this in the future. The drawing tools are some relatively simple tools for mechanics diagrams, and then some more non-trivial things for drawing field lines, circuits, and geometric optics. Okay, the overall point of view of what we've been working on is that interactivity needs to serve a purpose in lecture notes. I think too often a lot of interactivity is done in a trite way, where you animate something that doesn't need to animate. So you see a girl falling from a tree with something being shot at her, and it's trivial and not making a point to merit the interactivity. So yeah, cute, trivial things need to be avoided. There's got to be something critical in the pedagogy that you're illustrating. Things like the Wolfram demonstration project and the PhET simulations, and they're from the University of Colorado. They're quite good, both are quite good, but they're standalone things. They wouldn't integrate into a lecture as cleanly. They'd be things you could sort of take a break from the lecture, show these, okay, let's show this PhET simulation, let's show this demonstration. But the intention of this interactivity here is it should be integrated directly into the lecture. It's important to target those subtle points that students struggle with and don't just introduce interactivity for the sake of interactivity. A style point I try to make is that the lecture notes should print reasonably as a PDF, even if, so you shouldn't see controls on the manipulates until you click on it, and the manipulate should make sense as a standalone thing. Okay? As for the current state of the notes, I think they're complete as far as the basic development of the material, meaning all the equations are derived, etc. But they're far from complete in terms of figures, both interactive and static. And to kind of evolve this into something bigger, like becoming an e-text, there needs to be a lot of worked out examples and interactive figures added to those. So there's a lot more that needs to be added to this to kind of expand the project. These are the course link pages. Hopefully I'm connected up here. And for each chapter then, there's a CDF, a PDF, and then problems and solutions. Okay, let's get into some of the examples. The first is oscillatory motion. So here's a fairly simple manipulate with a mass spring system. Is it trivial to animate a spring? I mean, is it worth doing pedagogically? I think whenever you connect motion to a graph at this level, it really is essential. So for them to see that this graph is associated with that motion is critical. And then the usual manipulate things, you change the parameter and see how that affects it. This is sort of manipulate 101 right here, change some parameters. It's pretty trivial as far as mathematics is concerned, but it makes a useful point. Same spring example. This is making a critical point that when you hang a mass from a spring, the effect of that is to shift the equilibrium position, and then you get simple harmonic motion about that new equilibrium position. Well, that can take a fair bit of text to describe that, but a simple picture works. So you stretch this from equilibrium, release, and you get oscillatory motion about the new equilibrium position. But notice that the original diagram sort of makes sense in itself. The diagram looks clear. If you're just going to print this as a PDF, it makes sense. The wave examples are more, or the wave chapters are more non-trivial here, so let me jump quickly into them. Okay, so first a brief discussion of stress, strain, that stuff, and then into a discussion of waves. Okay, simple animation, but a critical point, I think, is being made by this. Oops. Okay, so you have a pulse of any arbitrary shape maintaining its shape and traveling at a fixed speed. Reflected pulses then travel in the opposite direction. More is discussed about the general solution of the wave equation as we progress here. Okay, consider a sinusoidally shaped wave traveling. Then to animate this, basically this is connecting y as a function of x with, at a particular x value, y as a function of t. So as the wave is passing, a point on this is moving in simple harmonic motion. This is relatively trivial, but I think it's not a big deal either. So it's just making the point that for 3D we have moving wavefronts, and this is describing what's going on. That these wavefronts are moving is not obvious to students sometimes from static diagrams. But this animation here is much more non-trivial. This is a very subtle point, what's going on with a pressure wave in a fluid. Okay, so when you open it up, you have different choices of waveforms, and the key point is that the molecules represented in blue are moving back and forth by a small amount, but yet the energy in the wave is being moved over large distances. Okay, it's a bit of an optical illusion, and it looks like the whole thing is moving off to the right. So by showing the equilibrium positions, it makes it a little bit clearer that these molecules are just moving back and forth, and the entire pulse is moving to the right. Can also show the pressure waveform. Pressure is the derivative of the displacement, so one is shifted relative to the other. Other waveforms can be pushed in. That's my favorite pulse shape. And notice how cool the derivative looks. It's a quite different shape. And then a standing wave as well. Okay, so this one figure, I think, is getting a lot of physics across. Okay? Okay, that's that chapter. And then the next wave chapter has some other interesting examples here. This is the Doppler effect. I'm amazed in looking at textbooks how many pages get dedicated to different examples and cases of the Doppler effect, where the source is moving, the object is moving, one is moving toward the other. The amount of pages, a student looks at that and just gets intimidated, thinking it's a hard topic. It's not. I mean, just choose a sign convention that makes sense, applies to everything, and then this diagram clearly shows what all the sign conventions mean. The sign convention I choose is positive is when the source and observer are moving toward each other. So the source is moving, putting out a wave. You can vary the source velocity. You can vary the object velocity, and notice you can vary the source velocity to the point where you get the shock wave and a sonic boom. And animating this does show what's going on. The frequency here is given as the general formula, but by varying these sliders, one can actually give a number for what these frequencies are. So so you see, as you move it, you see the speed, VO in terms of the V, VS as a multiple of V, and the frequency, the new frequency, to the observer in terms of the frequency of the source. Okay, so a lot's going on in that diagram. And it really saves a lot of text. That's the key point. Here's an example of the static figure telling the story briefly, and then it can animate to just show superposition as waves are passing. And you can try different cases, one flipped relative to the other. In this case, there's some critical point. If you pause and move the slider, you can see where the y is 0 for the whole situation. This is basically the same animation as at the beginning. Here's another example where you have a ring sliding on a frictionless rod. And in that case, the reflected pulse is not flipped. By the way, that's not a 3D diagram. It's a 2D diagram, and it's best avoiding 3D if you can. So this looks 3D, gets the point across, but it's actually a 2D diagram. Okay, so the pulse comes in, hits, reflects, and goes back. Oops. Okay, here's examples of a varying wave speed. The speed of waves on a string is the square root of the tension over the mass per length. The tension is the same on both sides. So if you have a heavier rope on one side than the other, where the rope is heavier, the speed is smaller. So here's an animation of that. And this is the proper solution to the one-dimensional wave equation with the appropriate boundary conditions. And then in this case, the reflected pulse isn't flipped. Standing waves, usual thing. You can write a standing wave as the sum of left moving and right moving pulses of the same amplitude and frequency. But that's difficult math for some of the students, but the animation makes it quite clear what's going on here. Things like show envelope function, that's just, if students are clicking that, they know what I mean when I say the envelope function. And then nodes and antinodes, that's just clearly making that point what the nodes and the antinodes are. So by just clicking around, students are getting a lot out of this diagram, hopefully. Okay, standing waves, I won't illustrate all of these, but the nice thing about this is you can really see the frequencies are changing as you're varying the mode here. So the m equals 1 is very slow, the m equals 8 is crazy fast. Okay, so a lot's going on with this figure, but you can see the gist of it quite quickly. Other cases considered, pipe with both ends opened, one end open, one end closed, but no need to get into that. Beats, you can vary the frequencies, the beat frequency. So you can see the two waves you're adding together, and you can play it just to make that point. This gets obnoxious if many people are doing it, but it does connect it to the actual sound. From the second semester course, here's an example of basic chapter on electric charge. A point that students struggle with greatly is continuous distributions and what it means to integrate over a charge distribution. Cal 2 is a prerequisite for Physics 2 at my school, so students should be pretty familiar with integral calculus. However, that means if given an integral, they know how to evaluate it, but they don't really know what an integral is. So they really struggle with this point. So here's a uniform line. The natural variable of integration, the natural dummy variable of integration is x because it's along the x-axis. The position vector r from the charge dq to the point is shown in green. And then we're dealing with 2 points, P and Pb. This shows the electric field. So you can see in the case of point A, the field is getting small as you get further away from it. And it shows quite clearly that for point B, that by symmetry, the fields are canceling. The x components of the fields are canceling. And you end up with something only in the y direction. Same thing, you can show the field here. This is the uniform ring of charge. Same deal, okay? Okay, let me get into the tools here. I'm running short of time. Okay, so the mechanics tools I don't think are that big of a deal. I think the spring's kind of cool, but most of the tools in mechanics are just like labeled double arrows are useful, labeled vector arrows are useful things, but this is the sort of thing most experienced Mathematica users probably have developed their own tools for. The more non-trivial tools are for drawing field lines. What's the Mathematica command, field plot or vector field, or I forget. But it doesn't draw these continuous curves that you want for a physics diagram. Okay, so you want the field lines to begin at positive charges, end at negative charges, and not start and stop in random places. This is just using ND-solve and integrating the unit vector of the electric field. You can plot these things, and then the arrows are placed by some algorithm and can be chosen where they, and you can specify where the arrows end up. This is a tool for drawing circuits, resistors, capacitors, inductors, DC voltage sources, AC, diodes. And the gist of the program is, draw circuit is the command. So you list the nodes, and then you list the nodes, pairs of nodes and what's connected between them. There can be multiple things, resistor, capacitor, inductor, etc. In between one pair of nodes. So this is similar to how like graphics complex keeps track of positions. Just to show what's going on with this, and I don't really like this diagram too much. I think the resistors are too big for the diagram. So the way I would play with that is just it rescales everything. So just put a spacer in before and after. And then that shrinks the size of these things. It looks a little better. Okay, just to show what's going on, I wrap this in a manipulate, and as you move these things around, the resistors rescale themselves so they all stay the same size. You can specify the number of turns for a given resistor. Just some other examples. You can offset things like a meter. So the command for that is offset points. So that offsets it by certain parameters, and then you can put whatever you want in there, or whatever series of things you want in there. So that's quite useful. And here's just a complicated diagram using this stuff. Essentially everything in this diagram is using this except for the plus and minus signs over here and these x's, okay? They're added in on top of the whole thing. But other than that, the whole diagram is drawn with the draw circuit command. And then for geometric optics, here's the chapter on this, just many examples of ray tracing. Here's rays hitting a spherical mirror. Parabolic mirror, notice the rather severe spherical aberration. Plane waves off the central axis, and then this whole thing can be wrapped inside a manipulate. So as you move around, go off to infinity by just going over here. And when you come in here, you can see the object and image positions. Okay, so the field plot program can trace rays backward to a fixed point to show a virtual image, or forward to some fixed stopping point to show a virtual object. And then standard sort of ray tracing pictures, mirrors and lenses. Same manipulate, but for a convex mirror. Let's see, and let's then look at the code for this. Okay, so there's a lot going on in this picture, but actually the code for the ray tracing program is just this part here for trace ray. So spread directions just means you shoot off in a given direction. It hits a circular interface at x equals 0. So this is not, sophisticated like some optical program. It's just designed to be for drawing this type of diagram. Okay. So it hits a circular interface, tells it to do something. The next circular interface, in that there's the trace ahead. Stopping at vertical equation SP1, so what that is the condition showing the virtual object stopping over at that point, so to trace the rays forward at that point. Okay, looking at the time, I should be finishing up, so let me conclude here with where we'd like to head with this. We're pursuing grant funding to turn this into an open source interactive e-text. That's the goal, to share everything, okay, including the tools. We don't have that grant yet, so I don't know. But if we don't get it, we'll be passing around a hat, I guess. But so the goal, the ambitious goal, is to turn this into an open source interactive e-text, and people can just edit it at will. I think the interactivity would be useful for other people, the interactive figures, and the drawing tools would be of significant use, hopefully, as well. So that's it, and thanks for your time.